In our search for a solution to global warming, there are many different paths that we could take. One approach that is worth looking into is climate engineering, or attempting to change the climate of our Earth on a global scale. Some types of climate engineering focus on increasing the Earth's albedo, or reflectivity. For example, cloud seeding involves spraying particles into the atmosphere to promote cloud development or spraying water vapor into existing clouds to make them denser and more reflective. This could decrease the amount of sunlight reaching the surface. A similar solution would be to release sulfate aerosols into Earth's atmosphere. These aerosols would reflect sunlight, increasing Earth's albedo and potentially mitigating global warming. A different type of climate engineering, known as space-based geoengineering, also aims to reduce the amount of sunlight reaching the Earth. However, in space-based engineering, the goal is to block solar radiation before it even reaches the Earth's atmosphere. One such space-based engineering solution is a space sunshade. So what exactly is a space sunshade? A space sunshade is a satellite or group of satellites designed to reduce Earth's insolation, otherwise known as the amount of light which strikes the Earth. The idea, similar to other climate engineering solutions mentioned, is that reducing the amount of solar radiation reaching the Earth could help reduce global warming. 3 specific ideas have been proposed as possible ways of building a space sunshade. One is a cloud of spacecraft, each of which would have its own control mechanism. A second would be a Fresnel lens, a thin-filmed lens designed to diffuse sunlight. The last method would involve a large diffraction grating, a fine mesh of hundreds of wire per inch designed to refract light. The first idea involves a cloud of small spacecraft. 18 trillion flyers, each weighing roughly 1 gram, would be comprised of 3 distinct parts: a transparent film to reflect sunlight, navigational prongs, and a control hub to control its motion. The cloud would be located at the L1 Lagrange point, which is a point where there is zero acceleration between an object, the Earth, and the Sun. Placing the cloud at the L1 Lagrange point would ensure that it stays more or less in place for a long period of time. The cost of this method would be roughly $5 trillion, or 7% of the global economy last year. The left graphic illustrates the placement of the cloud relative to the Earth and Sun. The right graphic shows a time-averaged view of the blocking caused by the sunshade. The center dashed circle is the Earth. The blocking varies with time due to the wobble of the Earth. Since the flyers would be small, they could be sent into outer space in stacks and would not need to be unfolded or assembled in orbit. Mass-producing the flyers would also be simple and cost-effective. Unfortunately for the design of this project, each of these flyers would act similarly to a solar sail. A solar sail is a flat surface in outer space which generates acceleration by being hit with photons by a nearby star. The constant bombardment of protons by the sun would cause different regions of the cloud to shift due to different radiation pressures. This requires each flyer to have radio transceivers and 2 cameras in order to determine their position relative to the Earth, the Sun, and each other. The system would require a complex algorithm in order to control these shifts and ensure it stays in place. There is also a chance that no longer functioning flyers could find their way back to Earth and interfere with the system of communications and defense satellites already in place. Another space-based geoengineering strategy was proposed in 2004 by astrophysicist and science fiction writer Gregory Benford. His radical proposal was to construct a Fresnel lens 1,000 kilometers across with a thickness of only a few millimeters, and to place it at the Lagrange equilibrium point. The overall concept of the Fresnel lens is inherently sci-fi-like. In fact, a very similar situation was presented in Arthur Clarke's 1953 sci-fi novel, Childhood's End. Note that in this slide's visual, the lens is heavily exaggerated in size. The concave Fresnel lens would ultimately diffuse sunlight away from the Earth, reducing total insolation by approximately 0.5 to 1%, which would compensate largely for increased anthropogenic CO2 levels. According to Benford, the project could be completed with current technology with a cost of about $10 billion upfront, plus an additional $10 billion over its lifespan. Some advantages of the Fresnel lens in comparison to other space-based geoengineering schemes is that $20 billion is not ridiculously expensive for such a huge project. Furthermore, according to climate models from McKean's research on space-based geoengineering, The result of reducing solar insolation would largely make up for increased atmospheric carbon dioxide. A giant Fresnel lens would be able to control global mean temperatures, preventing a major disruption to ocean currents and curtail global sea level rise. Disadvantages of such a project, however, include that solar winds pose a threat of displacing the Fresnel lens. Furthermore, critics of the lens warn that there is to be less distinctive diurnal cycle and lower temperature gradients with latitude, as the effect of solar insolation would be pronounced at the equator. Beyond that, there is still the technological challenge of fabrication, development, and maintenance. The third idea involves a diffraction grating, which again is a fine mesh with hundreds of wires per inch. This grating, hundreds of kilometers in diameter, would be flown into space and placed at the Lagrange point, the point where gravity from the Earth and Sun are equal. The diffraction grating would filter out 1 to 2% of incoming solar energy. This would mitigate the effects of increased greenhouse gases while not affecting life on Earth. The diffraction grating can be easily adjusted once deployed to filter out different amounts of solar energy. Once deployed, the grating will require little to no maintenance to perform. Unfortunately, the technology does not yet exist to make a diffraction grating of the size required. Accounting for advances in technology, the project would cost somewhere between $7 and $10 trillion. This chart shows the expected amount of Earth shadowing one could expect as a function of shield radius. For the desired amount of sunlight reduction, a shield of roughly 1,000 kilometers would be needed. Though the space sunshade method would be feasible to implement, and there are many different ways it could be done, critics argue it is not the most cost-effective or time-efficient way to mitigate global warming. The amount of money spent on a space sunshade would be better spent on other global climate change solutions. Additionally, other solutions could be put into action much more quickly than a space sunshade could be manufactured and launched. As well, even though a space sunshade might mitigate global warming, it would not solve the other problems, such as ocean acidification, problems related to high emissions of carbon dioxide and other pollutants. These systems may inadvertently reduce society's incentive to change their use of fossil fuels and adopt renewable energies. As such, this type of system treats only the symptoms of climate change and does not curb or dissuade the causes.